Hello, welcome to Optical Fiber Communication Laboratory Manual. Today we'll discuss practical one. Please, if you're not like, subscribe or press bell icon, then please do it. There is a sample of certificate from Government Engineering College, Bhavnagar with the form of the detail with the student, branch, semester, engineering department, enrollment number, and subject code with subject name and which year and submission date is mentioned with the staff in charge, head of department sign. Then index is prepared with the serial number, title of experiment, page number, date, sign and remarks. So today we will discuss about first practical, that is to write Scilab code for given examples of optical fiber waveguide. The first practical is optical fiber waveguide. Aim is to write a Scilab code for given example of optical fiber waveguide. Software is Scilab 6.1.0 is version. So first, what is optical fiber? An optical fiber is a hair-thin cylinder fiber of glass or any transparent dielectric medium. Waveguide. Waveguide may be used to carry energy between pieces of equipment or over a longer distance to carry transmitted power to an antenna or microwave signal from an antenna to a receiver. Waveguides are made from a copper aluminum. These metals are extracted into long rectangular or circular pipes. An electromagnetic energy to be carried by a waveguide is injected into one end of the waveguide. The electric and magnetic field associated with the signal bounce off inside of wall backs and forth as it progresses down the waveguide. Next, we try to understand reflection. In simple terms, reflection implies the rebounding of light, sound, heat, or another object back to the source without absorbing it. It alters the direction of the beam of light when it falls on the plane amidst two media, so that the ray goes back to the medium in which it is generated. Okay, so the law of reflection says the angle of incidence is identical to the angle of reflection. And second is the ray of incidence, ray of reflection, and the normal drawn at the point of incidence to the mirror occurs at the same plane. These two principles are opposite to all kinds of reflecting planes. Reflection can be of two types. First is the regular reflection and second is the irregular reflection. Regular reflection known as a specular reflection also, which occurs when the beam of light falls on a rectangular polished and smooth plane such as metal or mirror, reflects light at the same angle as it incident to the surface. Irregular reflection, also called a diffused reflection, which takes place when the beam of light is incident on the rough surface and reflect light in diverse directions. Refraction. Refraction can be understood as the phenomena of light wherein the wave is diverted when it passes diagonally through the interface between two media of different densities. It refers to the shift in the direction and the speed of the beam of light of radio waves because of the change in transmission medium. Refractive index is the ratio of the angle of incidence to the angle of refraction. It ascertains the speed of a ray of light in the new medium. The denser the medium, the slower is the speed of light and vice versa. Refraction index is defined as small n, that is equal to c by v. C is the speed of light in free space and v is the velocity of light in non-conductive medium. This is the example for reflection, that ray is incident and it is reflected back in the same medium, air. While in the refraction, ray is incident in air medium and is refracted to the water medium. Okay. Snell's law, the ratio of the sine of angle of incidence to the sine of the angle of refraction is a constant for the light of a given color and for the given pair of media. Snell's law formula is expressed as n1 sine phi 1 that is equal to n2 sine phi 2. Total internal reflection. A ray of light passes from a medium of water to that of air. Light ray will be refracted at the junction separating two media. Since it passes from a medium of a higher refractive index to that have a lower refractive index, the refracted light ray bends away from the one. This is the kind of example, total internal reflection, totally back to the same medium. At the specific angle of incidence, that is theta 1 or theta 2, the incident ray of light is refracted in such a way that it passes along the surface of water. The particle, like this passes of surface passes from the water. So this is at around 90 degree. This particular angle of incidence is called the critical angle. Here the angle of refraction is 90 degree. Critical angle is measured is equal to sine phi, that is equal to n2 divided by n1. This is the incident ray, this is the refracted ray. So when the angle of incidence is greater than the critical angle, the incident ray is reflected back to the medium. We call this phenomenon as a total internal reflection. Acceptance angle and numerical aperture. The acceptance angle is a function of refractive index of the core and the clouding material. Acceptance angles, that is defined as theta I, that is equal to sine inverse numerical aperture. The sine of the acceptance angle is called the numerical aperture. The numerical aperture of an optical system is a dimensionless number that characterizes the range of angle over which the system can accept or emit light. Na can be also defined as like Na is equal to n1 2 delta or under root of 2 delta, where delta is equal to n1 square minus n2 square divided by 2n square. For small angle, the solid acceptance angles in air, theta is given by theta is equal to pi theta s square is equal to pi sin square theta. The acceptance angle for skew ray, that is theta of A is equal to sine inverse Na by cos gamma. And normalized frequency is referred as V number in fiber optics. The normalized frequency is a dimensionless quantity that is denoted by the symbol V, and which is given as V is equal to 2 pi divided by lambda under root of n1 square minus n2 square, where A is a waveguide core radius, L is the wavelength in vacuum, and n1 and n2 are the maximum refractive index in the core and a refractive index of the homogeneous cladding respectively. Here note that difference between the square root of the n1 square and n2 square is by definition the numerical aperture of the fiber. This one, n1 is equal to n1 square minus n2 square. So you can also put here numerical aperture. For a multipole fiber, the mode volume of that fiber, which is approximate number of bound mode within that fiber, is directly proportional to the normalized frequency. For a single mode fiber, it is required that the normalized frequency satisfy the condition V is less than 2.4048. For a step index fiber, the mode volume of that fiber is directionally proportional to the square of the normalized frequency, that is V square. Number of mode traveling in the fiber. The total number of mode traveling in a fiber depends on the V number and is related as for step index fiber n is equal to V square by 2, or for gate index fiber n is equal to V square by 4, or m. Mode is you can define as a mode m capital M. Okay, now we discuss the example that is given in the John M. Senior book, and now we will solve this example with the help of Scilab. So same example we have calculated using Scilab that is given in the John M. Senior book. The first question is, a silica optical fiber with a core diameter large enough to be considered by a ray theory analysis has a core refractive index of 1.50 and cladding refractive index of 1.47. Determine the critical angle at the co-recording interface, the numerical aperture of the fiber, and the acceptance angle in air for the fiber. Okay, so this is given data in one, that N1 and N2 is given, critical angle we have to find, numerical aperture we have to find, and acceptance angle we have to find. So for this calculation, we will use the equation number 1.3, 1.4, and 1.5. Okay, so this formula 1.3, 3, 4, and 5. Okay, so now we try to, this is given N1, N2. So first sine inverse N2 by N1. You have to calculate this in terms of degrees. So that's why we converted with the help of 180 divided by pi. Then numerical aperture is the square root of N1 square minus N2 square. So SQRT function, that is well defined in Scilab. That is theta A, that is acceptance angle, that is equal to sine inverse NA. 1 second you have to calculate in terms of degree, that's why 180 divided by pi. So let's try to run this program. And this is the final displaying the result, printf of this critical angle at the co-recording interface, then numerical aperture for the fibers, and the acceptance angle in the air for the fiber in degrees. Okay, so what is my suggestion, that first you have to try to do this kind of example with the help of notebook, and then you can try it with the help of Scilab program. Okay, this is the result. You can see this is the comment line. We already discussed this kind of use of comment in the Scilab as well as method. So and then finally the result, you can see that when we print f, then critical angle of the curve is 78.5 degree. Then numerical aperture for the fiber is 0.3 knot, and printf, the acceptance angle, that is around 70.4 degree. One other facility is this, you can also write separate program. So click on this launch sign out, then type your program. I already copied the program, so I just paste it. So this is a separate file is prepared. In matlab.m, here in scilab.sci file will be created. So save for your reference. So let's practical one. You can see .sce is the extension of this particular file. So save it. And then here execute command is given. So you can click on this execute. This is a comment with the double backslash. You can see the comment line in the green, then variable in the red color, then function in another green color, blue color. So this kind of different colors are there. So we can differentiate all the different kinds of things that we have used in Scilab. So this is a simple equation based for implementation. So now click on execute, and you can see this is the result. Okay, I think you will be confused. So another command is first clear. This is the variable browser, command is T, and this is the file browser. When you click clear, you can see here variable browser is clear. Okay, so if you want to clear this all the screen, then CLC. Okay, yes. Okay, so all the clear command console window is clear. This is the console window. So 1 second we run this program, so you can see the result better. Okay, so this is the execution of this critical angle, then numerical aperture and acceptance angle in air for the fiber. This is the result. Then second example is typical refractive index difference delta, that is for optical fiber designed for a long distance transmission is 1%. Estimate the numerical aperture and the solid acceptance angle in air for the fiber when the core index is 1.46, it means N1. Further calculate the critical angle at the core trading interface within the fiber, and it may be assumed that the concept of geometric optic hold for the fiber. So same kind of formula we will use, equation 1.3, 1.4, and 1.5. N1 is given, delta is given, this relative refractive index difference to delta. Then numerical aperture, so N1 square root 2 delta, then is the for the solid calculation of the solid acceptance angle, that is zeta, that is n square. Then for critical angle, the core clearing intercept difference, that is n2 is equal to n1 multiplication of 1 minus delta, and phi c, that is equal to sine inverse n2 divided by n1. And finally, for result seen in the window, then we use printf function, and whatever we have to write, that we will display at the result side. So numerical aperture of the fiber is 0.21, solid external angle for 0.13 radians, and the critical angle for coordinating interface for the fiber is 81.9 degrees. So we can just verify this program with the help of Scilab also. So then you can see once again, there's a variable, then function, a comment in green line, then click on execute. Save and execute, yes. Then you can see, okay, so this is executed, the program. Earlier variable browser is created, so they are as it is. If you want to clear that browser, then you can also write once again clear, so it will be clear. CLC will clear the console. Are you sure you want to clear the console? Yes. If you want to click this, then next time will this message not will appear, so clear the console. Then third example is an optical fiber in air has a numerical aperture of 0.4. Compare the acceptance angle for a meridional rays with that for the skew rays, which change direction by 100 at each reflection. So that equation already given in 1.7 that we will use. You can see here 1.7. So okay, this equation will be used for the skew rays. Okay. So okay, so this equation sine inverse Na cos gamma. The acceptance angle for the skew in degree, that's why 180 pi is used. Then for theta, acceptance angle for meridional ray, that is sine inverse Na into 180 divided by pi, and this is the result. That's it. So let's run this program in the Scilab, and here's the result that is produced with when we have run this program in the Scilab. So now execute this program. Okay, so program is executed. You can see the acceptance angle, acceptance angle for skew ray, and acceptance angle for skew ray is about 50 degree greater than the meridional ray. So this is greater than result that we printed. CLC, just clear the console. This time message is not displayed because we already click on that particular dialog box. And if you want to clear the variable browser, you can just type the clear. Okay, then next is on example 4, there is a multiple step index fiber with a core diameter of 80 micrometer and relative index difference of 1.5% is operating at a wavelength of 0.85 micrometer. If the core refractive index is 1.48, estimate the normalized frequency for the fiber and the number of guided mode. So in this case, we have used equation for the capital V and capital M. There is a mode number. In this case, step index is given, so m v square by 2 formula will be used. If this equation 1.8 and 1.9 will be used, so this is the equation of v number. So yes, v is a 2 pi lambda divided by n1 square and 2 square, and m, this is m v square by 4 step. If it is graded, then v square by 4. Yes. So this is given that core diameter delta operating wavelength and find V and M. So just we have used this equation. This is the core for first we have to use the radius, so d by 2, diameter by 2. Then V normalized frequency. Then use of this number of guided mode V squared by 2, and this is the result with the help of printf function. Okay, so this is just equation that we have used to run this particular example. Save and execute. Okay, save, and it is executed. Okay, so the normalized frequency of fiber is 75.8, and the number of guided for the fiber is 2873. You first, as per my suggestion, you have to first calculate with the help of pen and notebook. These examples are already given in the John M. Senior book. Then you should practice on the Scilab. Okay, so question 5 is a graded index fiber has a core with a parabolic refractive index profile which has a diameter of 50 micrometer. The fiber has a numerical aperture of 0.2. Estimate the total number of guided mode propagating in the fiber when it is operating at the wavelength of 1 micrometer. So in this case, once again, use of V and here graded index fiber. So just formula change, one is V square by 4. So here V square by 4 will be used because gradient index fiber. So whatever the given, then we have to assign with the help of variable. Then for displaying the result, we have to write printf function, and this example can also check with the help of Scilab. First, okay, save this program. So you can also save here also, okay, or otherwise just click it when if you're not to save, then execute this program and you can see the result. Okay, so number of modes supported by fiber is 247. Okay, so CLC once again clear. Then question 6, estimate the maximum core diameter for optical fiber with the same relative refractive index difference, delta is same, and core refractive index and one is given, may be suitable for the single mode operation. It may be assumed that the fiber is operating at the same wavelength. Wavelength is given. Further, estimate the new maximum core diameter for a single mode operation when the relative refractive index difference is reduced by a factor of 2. Okay, so we have to just see the effect of change in size of core diameter. So use equation 1.8. So V is given, lambda is given, N1 is given, delta is given. So first, the maximum core radius for the optical fiber with delta of 1.5. Then this is the first one. Then we reduce the reduce, what is we reduce the parameter? Yes, that maximum core diameter of single operation when the relative refractive index difference is reduced by a factor of 10. So when it is reduced by a factor of 10, so what is the effect of the final result? That can be seen. The delta is equal to, now delta changed by 10. So A2 is equal to V to lambda 2 pi n square to same formula, but here just the value of change is delta. So now A2 will be changed. So we have to see the result. What is the first case A1, and when we change the delta by factor of 10, what is the result in A2? So just try to run this program with the help of Scilab. So this is it. Green first case delta is 0.015, then second time delta is reduced by 10. So in this case, what is the A2? So okay, let's try to run this program. So run this program and you can see the result. Okay, so the maximum core diameter of the optical fiber with delta 1.5 is 2.5 micrometer. And the new core diameter for a single mode operation when the relative refraction difference is reduced by 10 is 8 micrometers. That means the first case it is 2.5 micrometer. In the second case it is 8 micrometer. So the value of A is increased in the second case. Now next is okay, so from the above experiment, we can to know about the what is optical fiber, what is waveguide. We can also know the different technology like reflection, critical angle, incident angle, Snell, slow, acceptance angle, numerical aperture, skew ray, normalized frequency, and the number of guided mode. We also written the Scilab code for numerical examples. Here demonstrated examples are given in the optical fiber communication principle and practice, John M. Senior, that is Pearson publication and third edition book, and example numbers are 2.1, 2.2, 2.3, 2.4, 2.5, and 2.6. Thank you. Once again, request to like, share, subscribe, and press bell icon to receive our new videos, and do comment whatever need any kind of suggestion, then definitely that will be improve in the next video, upcoming video. Thank you once again very much.